In this video, we will look at some basic logic decoders. We will look at what are logic decoders, where are they used, how can they be used, and finally we'll give a quick demo. So what is a logic decoder? In its simplest form, it's a logic IC or circuit that will generate specific, unique outputs based on a specific input. The most common ones found are the 74LS139, which is a 2 to 4 line decoder, or the 74LS138, which is a 3 to 8 line decoder, and sometimes you'll find the 74LS154, which is a 4 to 16 line decoder. If you ever opened an old computer from the 70s or 80s, it's very likely that you'll find one or more of these devices inside. The 74LS139 is a dual 2 to 4 line decoder. This means the device contains two of these decoders. We've highlighted one of them in yellow so you can see what we mean. You can see from the images in the pin connection, and we can also see our internal logic diagram. We will cover logic gates in a later video. Notice that each decoder in the 74LS139 has only one enable line. When we look at the other chips, we will see that they will have 2 and 3 lines. Each of the outputs are active low. This is designated by the little circle on the output. This means the output is in its active state when the signal goes low or goes to 0. Otherwise it'll be high. This chip allows us to control 4 devices based on 2 inputs. 2 binary lines gives us 4 unique states, and this is what the decoder does. It allows us to control each output based on a binary state. The 74LS138 is a 3 to 8 line decoder. Notice there are 3 lines that control the enable signal. This allows for more complex circuits to control the decoder. Notice the level of complexity in the internal logic has increased to that from the 74LS139. The 74LS154 is a 4 to 16 line decoder. There are only 2 control lines for the enable. Notice the level of complexity of the internal logic has increased when we compare that with the 74LS138. It's not uncommon to see 2 74LS138 decoders linked together to generate a 4 to 16 line decoder. This would mainly be a cost cutting exercise, as the 74LS138 are very cheap compared to the 74LS154. So where are they used? As mentioned earlier, these chips were found in many computers from the 70s and 80s, before programmable logic ICs such as PALs and GALs were used. The most common area you would find these would be for address decoding and memory mapping. This is where the computer's memory was divided into various segments, and the manufacturer wanted to ensure that only certain devices would respond when the CPU requested a specific address. These devices were also used to switch banks of computer memory in and out of active address space. You would also find them if you wanted to control some I/O. If you wanted to light 8 LEDs, you would only need 3 lines to send the data instead of 8. Let us assume you had a computer with 32K available RAM that could be accessed by the CPU, which was not uncommon for most home computers in the 80s. If you wanted to expand this out to 128K of RAM, we could have 4 by 32K RAM chips, but only one RAM chip could be active to the CPU at any one time. We could use a 2 to 4 line decoder to enable one of these 4 RAM chips at a time so the CPU can access it. In this demo, we will use one part of the 74HC139. The 74HC139 is a CMOS version of the 74LS139, but more about that in a later video. In this demo, we'll have 2 buttons on our input, and we will inspect our output using a logic analyzer. In keeping with the retro style of these videos, we will be using an old 8-bit logic analyzer to view both the input and output levels of the 74HC139. The 74HC139 is connected as such. VCC is connected to pin 16, ground to pin 8. The enable pin is connected to D0. Both the inputs for the logic decoder are connected to D1 and D2, and the 4 outputs of the logic decoder are connected to D4 to D7. We can see that the LEDs D4 to D7 of the logic analyzer are high. You may remember that I mentioned that these outputs for these devices have an active low. You will also notice that the enable pin is also high. We can see this on D0. When we change the inputs from high to low, we can see these change in the logic analyzer, but nothing will change on the output because the enable pin is not active. When we bring the enable pin active low, notice that the outputs will now change as we step through the various input states. Hope you found this of interest. If you watch some of the other videos where I repair some retro computers, you will see where I identify these logic decoders and how I can test them in place.